this webinar, you will actually receive CEU PDH credits, and I will be sending out a certificate to all attendees within the next couple of days. However, before we continue, I'd like to conduct a quick poll. Just want to get an idea of how many years have you all been working with psychometrics, just to see what level everyone is at here. And after we're done with the poll, I'll share the results. Okay, so I'll close the poll and then I'm going to share the results. And as you can see, it looks like a number of you actually have greater than 10 years of experience with psychometrics, which is great. And then the rest of you less than 10. So pretty experienced group here. All right, let's continue. So psychometrics. Psychometrics is so important to the design of buildings and in helping engineers design HVAC systems for all types of applications. It's vital for human comfort. I mean, face it, it's difficult to work in conditions where it's too humid or too dry. We look at this Psych chart here, you'll see that there's really a small area where it's actually comfortable for humans to work in. In fact, there's an entire standard called ASHRAE Standard 55, which specifies conditions for acceptable thermal conditions for human comfort. So psychometrics is really important for that. Now going back, it's also important for controlling the environment, whether we're talking a museum, a library, or any type of archival facility where the systems are quite complex. And a system for this type of venue is designed to control the environment for the preservation of these highly valuable artifacts or works of art. And also these HVAC systems that service these types of venues really need to be operational 24/7 and also require redundancy. Number 3, mission critical in hospital operating rooms. Hospital ORs are kept so cold that there is a risk of condensation from above, since the temperature often goes below the dew point of ambient conditions. Therefore, using psychometrics, it's possible to design systems where you have the proper humidity ratio so as to eliminate that condensation. And finally, many industrial and manufacturing companies use chilled water to remove heat from various manufacturing processes. So as the air or the process is cooled below the ambient dew point, condensation can occur, similar to what could occur in a hospital OR. Therefore, desiccant dehumidifiers can eliminate this condensation, and this will result in higher part quality and reduced cycle time, allowing manufactured parts to be produced faster. So all of this requires psychometrics and requires understanding what psychometrics is. So is psychometrics art or science? Well, in fact, I think it's both. Here we have a picture of a page in the ASHRAE Handbook Fundamentals, which includes the actual psychometric calculations. Now, these aren't the easiest to read or understand. However, taking all of these calculations and then creating a visually appealing chart like this allows you to plot simple and complex HVAC processes and, of course, visualize them. That makes it a much more powerful engineering tool. Even those outside the industry, even those who don't really even understand the word psychrometrics, can look at this chart and start to understand, what does it mean to have the ratio of water to air and how it affects, and how HVAC systems, how it affects the ratios and how it benefits, humans in terms of comfort, in terms of having safe conditions. So It really is amazing that you can take these complex, hard-to-read formulas and create a chart which allows us to visualize these processes. So the agenda. I want to give a brief overview of psychometrics. Now, for some of you, this will be a review, and actually, according to that poll, over 50% of you, it will be a review. However, many of you probably are young engineers, maybe entering the industry, so it's really important for you to learn the basics. You know, I've learned over the years never to assume I know everything, because I certainly don't. In fact, while doing research for this webinar, I learned and relearned a lot about psychrometrics. So the overview will be short, so just sit tight. Then after the overview, I'm going to actually demo the app. And the way I'm going to demo the app is I'm going to be doing examples. I have about 11 examples, and time permitting, we'll do all 11. And by doing these example processes, both simple and complex, we'll be able to learn how to use the app itself and also learn a little bit about psychrometrics. Then at the very end, we'll do some Q&A if time permits. And like I said, if you do have questions, enter it in the applet, and I'll attempt to get to them. So the overview. So the definition of psychrometrics. I'm sure most of you know this already. It's a chart or graph of the thermodynamic parameters of moist air at a constant elevation or barometric pressure. Now the genius behind this chart is that it allows HVAC professionals to visualize all types of processes for cooling, heating, humidification, dehumidification, and much more. Now the chart you're looking at here is at 0 elevation. This chart is at 12,000 feet elevation, which is about 9.3 inches of water gauge barometric pressure. Now before Psychrometric software made itself available on desktop and mobile, most engineers had to resort to using the 0 elevation chart published in the Carrier or Train or even the ASHRAE Handbook of Fundamentals. However, building designers, say in Denver, which is at 5,000 feet, would have some problems because the density of the air is a lot different up there than it is at sea level, say here in the Bay Area. So if you were indeed plotting processes in Denver using the 0 elevation chart, you would produce inaccurate results. However, with software and apps, you can immediately view a chart, just enter the elevation and it will alter the chart. So it is more appropriate for the elevation that you're at. So the components of the chart. The chart is made up of a bunch of vertical, horizontal, and curved lines. So here you'll see a vertical line, the dry bulb temperature. That's easy. It's the temperature of air as registered by an ordinary thermometer. Not too hard to comprehend there. The absolute humidity or moisture content is the weight of water vapor in grains or pounds of moisture per pound of dry air. It is also known as the moisture content or humidity ratio, and it is the horizontal line that you see on the chart. The wet bulb temperature. The temperature registered by a thermometer whose bulb is covered in a wetted wick and is exposed to a current of rapidly moving air, otherwise known as a sling psychrometer. And this is a diagonal line here. Enthalpy is the thermal property indicating the quantity of heat in the air above an ordinary datum. And once again, enthalpy is also a diagonal line almost parallel to wet bulb. The specific volume, this is the cubic feet of the mixture per pound of dry air, and it's represented in feet cubed per pound. It's pretty much a reciprocal of density, or 1 over the density. And it is also a diagonal line at quite a different angle than the wet bulb and enthalpy. The relative humidity is these curved lines, and it is an expression of the moisture content at a given atmosphere as a percentage of the saturation humidity at any temperature. So the relative humidity is what most people use to communicate how humid is it out. Oh, it's 50% humidity. And finally, actually the dew point is the temperature at which condensation of moisture begins when the air is cooled. And of course, the best example of this is a cold glass of water. If the temperature of the water is less than the dew point of the ambient conditions, then you will see condensation on the outside of that glass of water. So that basically means you're lower than the dew point of that ambient air. And finally, this sensible heat ratio protractor. And this allows the user to draw a sensible heat ratio line, and I will explain what that means in the next slide or two. All right. So some other terms. The saturation curve. This is where the air is 100% saturated, no matter what dry bulb or wet bulb temperature we're at. So along this curve, the dry bulb, wet bulb, and dew point are all the same at any one point. The apparatus dew point. I actually had to relearn this one. This can be a little confusing sometimes. The apparatus dew point is basically the coil surface dew point temperature required to accomplish cooling and dehumidifying. So as you can see from the simple psychrometric chart, that the air entering the coil is cooled to slightly less than 100% saturation. However, if you want to extract water out of the air or dehumidify, then you need to approach the 100% saturation curve, and that is what's called the apparatus dew point, which is here. Bypass factor. Some of the air flowing through the coil impinges on the water tubes or the fins and is cooled to the apparatus dew point. Some of the air passes through unchanged. So there's a percentage of air that doesn't even touch that coil. Sensible heat ratio. This is the ratio of the sensible cooling to total cooling, and it's useful for plotting the slope of the path that the supply air will travel. And in some of the examples later on, I'll show you exactly how that's done. And adiabatic cooling. It's also called evaporative cooling or constant enthalpy cooling. And this is the process of reducing heat through a change in air pressure caused by volume expansion. It's also called free cooling, since the sensible heat is being converted to latent heat without the help of any type of mechanical DX cooling. So let's look at a couple simple processes here. So we got the horizontal process of sensible cooling and heating, basically moving along this horizontal line here. So you can increase or decrease temperature. An example of that is passing moisture over a room space heater. Humidification, dehumidification is a vertical process here, involves the increase or decrease in the humidity ratio of air without changing its dry bulb temperature. So the sensible temperature stays exactly the same. However, the humidity ratio increases or decreases. Heating and humidifying, which is along this diagonal line here, involves a simultaneous increase of both the dry bulb temperature and the humidity ratio of air. Cooling and dehumidifying, down here, involves the removal of water from the air as the temperature falls below the dew point. Evaporative cooling or free cooling involves the cooling of air without heat loss or gain. Sensible heat loss is lost by the air is converted to latent heat in the added water vapor. This is also called free cooling since it doesn't require any mechanical DX cooling. Chemical dehumidification is down here. It's also called adiabatic dehumidification and is actually accomplished by passing air through a chemical absorbent like a silica gel, and some of the moisture is removed and the latent heat of evaporation is released. Therefore, the sensible heat increases, yet you get a lower relative humidity and humidity ratio. So by taking a bunch of these simple processes, we can create more complex HVAC processes, which are listed here. So complex psychrometric processes can involve basic cooling, cooling with reheat, cooling using an enthalpy wheel, DX cooling, the dehumidification, indirect and direct evaporative cooling, and many, many more types of processes. So, I'll be touching upon these complex processes in some of the examples that I'll be showing. All right, I want to make sure I have a few complaints here that people aren't hearing me. Can you all hear me? If any one of you, if you want, you can just enter something in the chat saying that you can hear me. But I do want to make sure that you can indeed hear me. Hear you fine. Great. Thank you. Okay, so let's continue. So now that we've defined psychrometrics and shown you some of the basic processes that can be plotted, let's look at some real-world examples using the Psychrometric Chart app. And by showing you these examples, we'll not only learn more about psychometrics, but also be demoing the app for you, showing you how to use it. And the way I'm going to do this is I'm going to show you a screenshot of the app in the PDF here that you're seeing. And then I'll show you the completed process in the app itself, and then I'm going to reconstruct it. And by doing that, I'll be able to show you all of the features of the app itself. However, before we continue, I do want to do another quick poll. Okay, let me share the results. So a little over half of you actually do not use any type of software, which is amazing to me, given that we're in the app world. So I'm hoping that this webinar will encourage you to use software, because it really does, it changes your whole outlook on psychrometrics. I mean, going from using that paper chart to using either a desktop or mobile app, it's like night and day, and I'm going to show you that fact. So it's good to see that about 45% of you indeed use software, and I'm hoping to convince the other 55% that you do need to indeed use some type of software tool, whether it's desktop or mobile. Okay, so let's continue. All right, so I'm going to start real simple. And like I said, I'm going to kind of give you, these are going to be simple examples. I'll give you what we're looking for, some of the initial conditions, and I'm going to show you how to actually do it in the chart itself. So in this first example, all we're doing is a real simple cooling process. We're at 0 feet of elevation. We're at 79 degrees Fahrenheit dry bulb, 65 wet bulb room set point. And then our outlet is 59 degrees dry bulb, 55 degrees wet bulb supply air, and we have 12,000 CFM of air. So this is how the chart will look. So let's now go to the simulator. Okay, so now what you see on your screen is the actual app. So indeed, I'm not showing it from my iPad itself, I'm showing it from my MacBook. And what's nice about designing mobile apps is we can indeed, simulate mobile apps on our MacBook for purposes of webinars exactly like this, and also purposes of doing quality assurance. So what you see here is what you will see on your iPad. So what you're looking at it in landscape mode, you can also use the app in portrait mode. It's probably better in landscape mode, so the chart can stretch out like this. So this is the chart, and this is the app. And what's nice about this is you can create a bunch of projects, and I have 11 example projects here, which I will be demoing for you, time permits. And you can create as many projects as you want and store them for later use. And I'll show you how to create new projects. You can also copy existing projects. So if you have a project a bunch of points and processes that you want to copy and alter just a little bit, you can indeed do that. And I will also show you that. So let's look at this chart here. So this is our basic standard chart at standard temperature and pressure. How do we know that? Well, down here is we have a bunch of buttons and icons, which allow us to change the chart and also change the behavior of how we interact with the chart itself. So I'm going to click this little gear icon, and up pops our chart properties form. And as the name implies, this allows us to set the properties of our chart. And there's a lot of properties of a Psych chart, starting with the minimum and maximum dry bulb temperature that the chart will display, and also the min and max, actually the max humidity ratio, increments for dry bulb and humidity ratio, and the altitude. So we can change this altitude, I think, all the way up to 10 or 15,000 feet. And it will automatically change our barometric pressure. Many of you have asked, can this chart be used to display metric units? Absolutely, because, you know, most of the world is not the US, and most of the world uses metric. So indeed, click SI and everything changes to metric. You can also alter the units for your temperature from Fahrenheit to Rankine or Celsius to Kelvin, and humidity ratio units between pound per pound of air versus grains per pound. Down here allows us to change the look of the chart. Do we want to display certain lines, including wet bulb, enthalpy, relative humidity, and volume lines? Then here we can change the color of the line. So you can change the color of the chart. And I'll show you in the various examples, we have changed the colors, and it does definitely changes the look of the chart. All right, so click Save. And here, as I mentioned before, we have a simple process. So I'm going to actually delete a point. And the way you delete a point is you select it and make sure, actually there's 3 modes you can be in this chart. There's the point mode, which allows you to plot points like this. Oh. Go back. Oh, there we go. So I can just plot as many points as I want. If I want to delete a point, I select it, and it's selected by a little round circle outside the block point, and you click the trash can, and it deletes the point. So if I select this point, delete. Select this one, delete. So I'm going to select this one and delete it. We also have the line mode, which allows you to draw lines or process lines between state points. And finally, the label mode allows you to display labels on the chart. So here we have our initial point. I'm going to double click that point, and now you see the properties of that point. So here we specify the properties as 79 degrees dry bulb, 65 degrees wet bulb. Down here are the remaining properties of that point. So there are a couple ways to change the value for this, say, dry bulb. I can go in and pretend it's my finger going in, and up pops the iPad keyboard, and then I can change the value if I want. In this case, I'll just leave it the same, click return. I can also move the slider control. So as you can see, as I'm moving my slider, my point is changing. And what's pretty cool about this is it's changing along a constant wet bulb temperature line. So let's go back to 79, and if you can't get to the exact point that you want, get close to it, and then enter 79. You can also change which properties you want to be able to change, enter values for. So in this case, I'm entering values for dry bulb and wet bulb temperature. Suppose I want to enter a value for enthalpy or relative humidity. So you'll see that this also changed above. The reason is there's certain combinations which you can't have. For example, you can't enter conditions for humidity ratio and dew point because they're both parallel horizontal lines. Therefore, there's no way to extract the other properties of a point if you're dealing with 2 parallel lines. So if you change one, you may sometimes see another change. So I'm going to change this back. dry bulb. Here we have humidity ratio. Change that again to relative humidity. Go in here. You change that to 50%. Okay. So let me go back, and let's go back to wet bulb. And I want to change this back to 65. So now we have 79 and 65. And here are all the other properties at that point. All right. So let's plot another point. I'm just going to plot it, and then I'm going to move it around. So if you remember, the second condition was 59 degrees dry bulb, 55 degrees wet bulb. So as I move this point, oh, what happened there? Some reason to change that. Selected that point. So I'm going to go back, and let's go to 79 and 65. Enough. Okay. So I'm going to move this point. As you can see, as I'm moving this point, up top, it's showing me where I'm at on the chart. We also have these crosshairs that kind of help us better see it. I can turn off this crosshairs by clicking this, and the crosshairs turn off. Do it again. Crosshairs are on. Now, what's nice about this, you can also zoom into the chart. And obviously on the iPad itself, you can use your fingers to pinch to zoom in. In this case, I'm going to use the keyboard, and I'm going to zoom in. And see how I'm zooming in like that? And then if I want to scroll, I click this option, enable scroll, disable scroll. So I can scroll and pan around. Let me zoom in a little bit more. And I can pan around. Now, if I want to be able to actually plot a point, I need to disable the scroll so I can move that point now. So now, by zooming in, I'm able to plot that point a little bit more accurately. So let's do 59 degrees dry bulb and 55 wet bulb. So let's move here, and then I'm going to move down. There we go. Okay. So now we've plotted our second point. Let me zoom out. I'm zoomed out again. So now I want to plot a point. Plot a line between the two state points. So I'm going to select the first point, and then I'm going to draw it to the second point. Now if I go back, select point, and select these point properties, it tells me the properties of my point, but it also tells me that I'm connected to point 1. And now I want to enter 12,000 CFM of air. And by doing that, it now shows me my total sensible and latent energy, and then my total energy, or total cooling, 373,000 BTU per hour. So we found our answer here. So pretty simple. All right. Move on to the second example. Okay. The second example is also fairly simple. It's an enthalpy calculation. So we want to find the enthalpy of supply air given the following conditions. And these conditions are 0 feet elevation again, 7,500 BTU per hour of sensible, 10,000 BTU per hour of total, cooling load, our set point 76 dry bulb, 64 wet bulb, which is our room set point, and then 55 degree of supply air condition. So we know the sensible, the dry bulb temperature of our supply air, but now we want to find out the one other property of that supply air. So how are we going to do that? Well, I'll show you. So let's go back to the chart. And I'm going to go down the project list, and I'm going to select example 2. So in this case, fairly same properties as our first example, 0 feet elevation, all the colors are the same. But I'm going to show you one new feature here. Okay, so let me delete this point. So we have our state point here of 76 and 64. And now what I'm going to do is show you a sensible heat ratio line. So if you remember from the example, we have 7,500 BTU are sensible, 10,000 BTU per hour of total. So that means our sensible heat ratio is 75%. So I'm going to click SHR. I want to display the SHR line. I want to pass it through point 1, and really it's only one point. But if you have multiple points, you can select from the one that you want the line to pass through. Then I'm going to enter 75%. I click Done. You'll see now we have our SHR line. Now I'm going to double click and create a point. And as I move, oh, that keeps happening. I'm not sure why it's selecting that point. But let me move that back. 76, 64. Okay. So as you can see, as I move this point, it moves it along the line, which is quite convenient. So I'm going to move this point along the line until I hit 55 degrees dry bulb. There I am. So I'm going to double click this point, and you're going to see now, here are my properties of that point that I created, and it followed the sensible heat ratio line. So therefore our answer is the enthalpy is 22.2 BTU per pound. So this is an example of how to use the sensible heat ratio line, and we got a number of questions during registration on this. So this is pretty powerful, and I'm going to show you a number of other examples on how to use the sensible heat ratio line. Okay, let's move on to the next example. Room relative humidity. So let's find the room relative humidity given, in this instance, we're going to be at 5,000 feet elevation, so Denver, Colorado. We have 22,000 BTU per hour sensible, 7,000 of latent. Our supply air condition is 63 degrees dry bulb, 90% relative humidity, and our room air set point is 80 degrees dry bulb. What will our relative humidity be? So once again, in this case, we're going to use that sensible heat ratio line and find that point. So let's switch to the app. Let's select example 3. I'm going to delete that. All right. So let's go into the properties. So here you see that I've changed the altitude to 5,000 feet. And as a result, it automatically changes my barometric pressure, which is 12.23 PSIA. I think that's right, yeah. And now I want to display the sensible heat ratio line. And in this instance, the sensible is 22,000, the latent is 7, so 22,000 over 29,000 is about 75.8. Click Done. So here's our line. I'm going to plot a point. I'm going to move that point along the line until we hit 80 degrees. There we go. I double click. And so our resulting relative humidity is 55.3%. Let's do something a little different here. Let's change the color of this chart. Let's change the background to red for our dry bulb and our humidity ratio to green. And you can see how it changes the color of our chart. Okay, let's move on to the next example. Mixed air conditions. A lot of you asked about how to calculate mixed air conditions. Well, I'm going to show you. So let's find the mixed air conditions of 2 air streams. We're at 2,500 feet elevation. Our first point is 90 degrees dry bulb, 50 degrees wet bulb, 3,500 CFM. Our second point, indoor return air, 72 degrees dry bulb, 50% relative humidity, at 2,500 CFM. Go to example 4. Here's our chart. Let's look at the properties of this chart. We're at 2,500 feet elevation. Okay, I'm going to delete these points. We'll leave this outside air point. So we're at 90 degrees. Dry bulb, 74.5 degrees wet bulb. 74 degrees wet bulb. And let's plot our other point, which is at 72 and 50%. Close enough. Now let's look at one thing. So we have the 3,500 CFM of air assigned to that point. Let's just enter 2,500 CFM of air for this point. Now we're going to draw a line between the two. So I click the line option. I draw a line here. Now I'm going to go back to point. I'm going to double click, and you're going to see a button that says create mixed air point. So what it's going to do is it's going to look at the point that it's connected to, look at the airflows, and then create that mixed air point. So I'm going to click it, and you'll see now that I've created that mixed air point. Double click it, and you'll see the properties. 6,000 CFM, and here are the mixed air conditions. Now some of you may be asking, when we do mixed air, do we take the airflows or do we take the masses? Well, we indeed take the mass, because if you think about it, the density of air at this state point versus this state point, it varies. It doesn't vary by much, but it does vary. So if we just did the ratio of the airflows, it would be a little inaccurate. Instead, we take into account the density of air at each point, calculate the mass of air, and then do the ratios to calculate our mixed air. So that is the more accurate way to do it, and indeed we do it that way. All right, let's move on to the next example. And I'm going to actually skip example 5 just because we have about 15 minutes left in this webinar, and we do have a couple more longer examples to look at. So I'm going to skip this example. This just showed you evaporative cooling along the constant wet bulb or enthalpy line, but I will be showing that to you in a more complex example in a couple of examples. Let's look at heating with humidification. So here we're starting to get some more complex examples. So what is the heat added in the final relative humidity given the following conditions? So we're at 2,500 feet of elevation. We have 2,500 CFM of air. 50-degree dry bulb, 40% relative humidity of entering air. Air is heated at 96 degrees dry bulb. Air is then passed through an evaporative cooler, or free cooling, until the temperature is 70 degrees dry bulb. So let me show you how this is done on the chart. Let's go to example 6. So you'll see we have labels added. So to add labels or edit labels, you click the label button, and then I can just double click this, and allows me to edit this label. And just click out to do it. So if I double clicked up here and said Psych chart, then it will display that. If I want to erase it, double click it and just go back and delete everything, and it's erased. So it allows you to add labels really anywhere on the chart, even outside of the boundaries of the chart itself. Okay, so let's look at the properties of this chart. We're at 2,500 feet of elevation. And what I'm going to do is I am going to delete, go to point, delete that point, delete this point. Okay, so we have our initial point. Even though it's number 2, it's probably because I drew it second, but let's just pretend it's the first point. So I'm going to double click the properties. So here's our starting point of 50-degree dry bulb, 40% relative humidity. Now what I want to do is I want to do a constant, I want to heat it to 96 degrees. So in other words, I want to move it along the vertical, along the horizontal, 96 degrees. So how do I do that? Well, I double click this point and I can say copy current point. What this does, it creates a brand new point at the exact condition of the old point, but now the new point is selected, so I can just move it and keep this constant. So let me go and I want to keep the humidity ratio constant. So those two change. So let's go back. Actually, this works. So we have dry bulb here, humidity ratio here. This is going to stay constant. However, I want to increase that dry bulb to 96 degrees. So I'm going to use my slider control, and as you can see, you can't really see it now, but as it comes out from behind the point properties form, you can see it's moving that point along the constant humidity ratio line and increasing that dry bulb to 96 degrees. And I can even go in here and just edit it, change it to 96 exactly. And there we go. So now we have 96 degrees. Next thing I want to do is I want to plot a third point that's along the constant enthalpy line. So how do I do that? I double click this point. And once again, I change it where at least one of the properties is enthalpy. One is dry bulb. Okay, so I want to keep that enthalpy constant, but I want to decrease that dry bulb to 70 degrees. And I didn't copy it yet. Let me copy that point. There we go. Has the exact same properties of the old point. Now I'm going to move this point. You can't see it behind it, this form, but you will see it once I close this form. But now I'm going to change it to 70 degrees. Click out, and you'll see now that here's my third point, and it is along the constant enthalpy line at our final requested point. So now let's draw some lines. Here to there, draw another line to here, and draw a third line to there. So the final relative humidity, we were asked to find the final relative humidity of our point. So if we just click the point properties, the final relative humidity is about 50%. Now, we also want to find out the heat that was added. So if we take the enthalpy here, which was 26.7 BTU per pound, and the enthalpy here, which is 15.6, you subtract the two, multiply it by 4.5 times our CFM of 2,500, we get about 116,000 here of total energy. So as you can see here, we heated and then humidified. All right, let's move on. Okay, for all of you that are not in the United States, I want to show you a metric example really quickly. So here we just have a simple mixed air calculation, similar to the one I did before, except now everything's in metric. So let's look at the chart. And you can also see the chart looks a little different, doesn't it? Well, what we've done here is we've actually changed the bounds of the dry bulb temperature, just to show you how you can indeed do higher temperature psychrometric calculations. So this is how the chart looks. So if I double click the properties here, you'll see that I'm using metric. My maximum dry bulb is 100 degrees Celsius, which is obviously 212 Fahrenheit. I'm displaying the humidity ratio in grams per kilogram. And then these are the properties of my chart. I'm not going to redraw this just for the sake of time, but if we double click on any of the point properties, you'll see that everything is in metric. So this can be used worldwide. All right, let's move on. Okay, let's do even a more complex HVAC process. DOAS, humidification. Dedicated outside air system, dehumidification. So what are we doing here? Well, we're starting with outside air at point 1. And we're passing that air through an enthalpy wheel. And on the other side of the enthalpy wheel is return air. So we're transferring some of the cooling from the return air to the outside hot air. So we're pre-cooling that air down to a state point number 2. Then we're DX cooling it all the way or almost to the saturation line. And then we're passing that air through a desiccant dehumidifier, a constant enthalpy process, down to our exact point here. So what are the final conditions of that point? And not only that is how much are we, what is the energy difference? How much of free cooling are we getting? And I'll show you that. So let's move on to the chart. Let's select example 8. So for the sake of time, I'm not going to recreate this process, but I am going to show you the properties of each point. So here, I double-click that. Here are the properties of my point, the outside air. The outside air is passing through an enthalpy wheel, and it's pre-cooling, free pre-cooling, all the way to this state point of 80 degrees and 59% relative humidity. Then at that point, I'm passing the air through a DX mechanical cooling all the way, or almost all the way, to saturation. And then my conditions here are 58 degrees, dry bulb, and 90% relative humidity. Then at that point, I'm passing the air through a desiccant dehumidifier. And if you remember from some of the prior examples, the way I'm able to move this final point along a constant enthalpy line is just by copying this point and then making sure the properties, the two properties that are displaying, is one is enthalpy, the other one is dry bulb, and then I move that copied point using the dry bulb slider here to my final set point of 70 degrees dry bulb, which is here. So here we're at 70 degrees, and these are the properties of our point. So the final condition is 42.1% relative humidity. Now, how much cooling did we save by doing that pre-cooling? Well, if we were going to DX cool all the way from the outside air point to down here without any pre-cooling using an enthalpy wheel, you do the math, subtracting the enthalpies times 4.5 times the CFM airflow of 5,000, you'd have about 34 tons of cooling. However, instead, we're doing the math from this point, taking the enthalpy from this point to here, it's only 17 tons. So pretty much half the tonnage requirements due to that enthalpy wheel. So by plotting the points on the chart, we're able to see that. Okay, so we have about 6 minutes left. I have 3 more examples. So obviously I don't have time for all the examples. I do want to show you one more example, and then I'm going to attempt to answer some of the questions that you either asked during registration or during this webinar. So let's move on. Here we have an example of dehumidification and cooling, which I'm not going to show you right now, but this is how it looks. But what I do want to show you is this very quickly. This actually came from the latest ASHRAE journal. There was an article in the ASHRAE journal talking about VAV system heat recovery economizers. So this is pretty complex. So basically what's happening here is we're taking outside air, we're doing indirect evaporative cooling, which is a constant humidity ratio process. In other words, no dehumidification really. And then we do, I'm sorry, that was indirect evaporative cooling. And then we do direct evaporative cooling, which I've shown you before, which is the free cooling, which also reduces our set point or our dry bulb temperature, but also increases our relative humidity. And then we do a minor amount of DX cooling at the very end. So this is showing you how doing indirect and direct evaporative cooling saves you a lot of energy, because you don't have to DX cool all the way from outside air to this point. You get a lot of free cooling in the process. So what is direct or indirect evaporative cooling? Well, let me show you a real quick example here. Explanation. Basically, what it is you're cooling that air, but you're not transferring the latent to sensible. So you're actually using a heat exchanger. So in other words, you're using a secondary airstream that is cooled by water, and then that secondary airstream passes through a heat exchanger where it cools the primary airstream. And the cooled air is then circulated by a blower. So you're cooling that air, but you're not taking out the latent heat. And then I already explained to you what direct evaporative cooling is. So a combination of those two is actually quite clever. It allows you to achieve exact psychrometric conditions and save a lot of energy. Okay, so I'd love to show you more examples, but we are running out of time, and I do want to answer a couple of questions. Here's a cooling with free heat example. So probably the most asked question of all was, is this psychrometric app available on other platforms? It is available also on Android. However, the functionality is not as rich as the functionality of the iPad. We did release a version of it, I think about 3 to 6 months ago. There is a version available for Android, but it does not have the rich functionality that the iPad version does. So it doesn't display the chart on your screen and allow you to enter the properties of the point and plot some processes, but there are a lot of features that it does not have compared to the iPad version. So just to let you know that. We do not have a version for the Surface or for desktop. There are other companies that offer desktop versions. We are solely focused on mobile. Another question was, and I've kind of addressed this already, is it available in metric? We got a ton of people asking that. Obviously, we saw that. You can use it in both English and metric units. What are the Psych equations based upon? Well, they're all based upon the equations in the ASHRAE Handbook of Fundamentals. I think it's Chapter 1, and the latest equations from the latest Handbook of Fundamentals, year 2013. A couple people asked, well, what are the advantages of using an app over pen and paper? Well, I hope by demoing this for you, I showed you the advantage. Pen and paper, you have that one chart at 0 feet elevation. This allows you to instantly change the elevation so you can see charts at any elevation, and it really makes a heck of a difference in the processes and in also the properties of air. Plus the fact that you can store so many projects. I didn't show this to you in the emulator because the emulator doesn't let us do it, but you can actually email a PDF of the chart that you see on your screen, and also an Excel or a spreadsheet of all of the points listed. So it allows you to open it in your favorite spreadsheet program and then work with it there. So you can indeed email your projects to yourself or to your client both as a PDF image and also as a spreadsheet file. So you can indeed do that. So there's a lot of power in using a mobile or desktop version where you can create projects, store them. You can copy projects over and over again, so you don't have to recreate the look of a chart that you want. You just can copy it. So there are a lot of advantages of an app like this over pen and paper. Also the fact that you can zoom in, as you saw in one of the examples, I zoomed in pretty far. It's pretty cool, so you can get an exact location of the point that you want to plot. And there are many, many more advantages of the app over pen, but those are a couple of them. Let me go through a couple of the questions real quick, and then I will end this webinar. There's actually a lot of questions here. so I can't address all of them. More of you are asking, oh, is there an iPhone version? There's not an iPhone version of this. The chart really is conducive to a bigger screen like an iPad. So no, we do not have an iPhone version of the screen. One person asked, are the lines snapping to the points? Yes, they are. So as you move that line, you get close enough to that point, it will automatically snap to it. You don't have to worry about it being exactly on that point. It will snap to it. One person asked, can reports be generated? I just answered that, yes. You can email a PDF and a spreadsheet report from the app. I could not show it to you in the emulator because for some reason the emulator doesn't display the email functionality, but in your iPad you can do it. One person asked, does the app do the sensible heat ratio map for you? No, it doesn't, because there's really no place to enter the sensible, the sensible and latent heat. So you kind of have to do the math on your own. But that is a good idea, and we may add a feature like that in the future where you just enter the sensible and latent or total, and it will do the math for you pretty quickly. All right, so we've actually approached the 11 a.m. Pacific time hard stop. So I have recorded this webinar, and I think this recording will be available on the ASHRAE YouTube channel. And what I'll do is after this webinar, I will make sure to email everyone who attended just describing where a recording of this webinar is located. Also, a lot of you are asking about this slide deck or this PDF, which I've gone through, and I think I can make it available to you. I do need to ask people at ASHRAE first, but I think I can make that available to you. And finally, a lot of you have asked, where do you get the app? Well, go into iTunes and just type in the keywords ASHRAE Psych and look for the launch icon, which you see here on your screen, and that's the app. It's $20. A lot of you asked what the price was. If you have any other questions, feel free to email me at sroth@carmelsoft.com. And that ends our webinar for today.